Hi everyone, welcome to our new course on complex analysis. So we're going to start off this course by discussing the complex numbers. So we begin complex analysis pretty much with the prerequisite of a multivariable calculus. Now, the reason we want to use multivariable calculus is because dealing with complex numbers is essentially a 2D puzzle. As we will see, complex numbers have real parts and imaginary parts. So it's essentially like dealing with a function of two variables. So what we want to do is we want to use what we've learned in multivariable calculus and create a system of calculus for these complex numbers. We really call it complex variables, but we will be using complex functions which take in complex inputs. And we will discuss, first, we will discuss the algebra. We're going to discuss the algebra of the complex numbers. And then we will take 2 units to discuss complex functions. And then after that, what we'll do is we'll discuss integrals. And then we will look at series or representations of complex functions as Laurent series. Finally, we will look at residue theory. And lastly, we will look at applications. You will note that applications of complex analysis are probably even more important than applications of multivariable or even single variable calculus in the fields of physics. The Schrödinger equation, in fact, deals with complex numbers, and that models all of the quantum mechanics that we know. And we will be using that to look at those equations. So you can really see how complex analysis is very important. And I would say that that is part of the reason why this course might not seem like as much of a pure math course, because we do want to look at the applications just because there are so many of them. Anyways, let's not get ahead of ourselves, right? We decided to talk about the complex numbers today, so why don't we do that? So I would like to start off with a problem that you've probably seen in your pre-calculus class. Consider the following equation such that x squared equals -1. Well, what this is really saying is it's asking if I draw a graph of the parabola, if I draw a graph of the parabola x squared, it's really asking us, when is this parabola equal to -1, right? That's a bit tricky because this never equals -1. We're never at -1, right? So it's asking us, if I want to solve the equation, I need to find a number whose square is -1. But we know that if I take any number, a, which is in the real numbers, and I square a, and a can be any real number. A can be a member from -infinity to infinity. It doesn't matter which. These should be open brackets, by the way. It doesn't matter if it's negative or not. If I take a squared is greater than 0. Okay? So that presents us with a problem because we have x squared equal -1. So how can I pick some x such that its square is -1? Obviously, what we can see here from our real point of view is that we have no solution. But what I like to think about is how we deal with a number like, I don't know, say the square root of 2. This number is not in the rationals. However, we still use it. It's a very important number in geometry. It's the hypotenuse of the isosceles triangle of length 1. But we use it as we do any other number. We could write 2 times the square root of 2, but it doesn't matter. This is a number we recognize. This is one that we don't, but we're still using it in our algebra. It still makes sense as long as it fits in. So what's stopping us from saying, hey, let there be a number such that its square is -1? So if I have some number such that its square is -1, then the number that we should get is the square root of -1. So what we're going to do is we're going to introduce the number I. I is going to be the number we're going to be dealing with so much in this course. I is equal to the square root of -1. Okay? That's probably one of the most fundamental statements I can make in this entire course. We have introduced a variable such that I equals -1. And our mission in this course is to see how much this screws up our theories of calculus. Okay? But again, let's get started with some algebra. So the number system itself can be summarized with this following definition. A complex number is an expression of the form a plus bi. So far, a and b are real constants. Soon they will be real functions, but so far they're real constants. So if I have two complex numbers, a plus bi and then c plus di, they can be equal only if a equals c and b equals d. We'll get into this later this video, but a is called the real part of this complex number and b is called the imaginary part because that's the coefficient next to that little number I that we have there. Okay, so we've introduced this new system. Now we want to see if it screws up our algebraic properties. So here are some of the properties and operations that we can do with complex numbers. So addition is going to work by component. It's almost like you have a vector, and we can just add and subtract this vector normally. So if I have the number a plus bi and c plus di, and I want to add or subtract them, I'm just going to take the real part of it and add it with the real part of the other number. Then I'm going to take the imaginary part of the first number and add it with the imaginary part of the second number. So we do it real part, plus or minus, plus the sum or difference of the imaginary part plus or minus the imaginary part. And then we tack on the imaginary constant at the end. Okay, that seemed fine. Let's try multiplication. So if I have two numbers a plus bi and c plus di, then what we can do is we can FOIL this expression. So if I take the first, that's a times c, so we've got that there. And then if I do the outer, a times di, okay? So a times di is a di, which we put here, but we multiply that after. And then if I multiply the middle, I get bi times c, so we got bc times I. Then finally, this is where it gets a little bit tricky. I got bi times di. Now normally we'd say that's like bdi squared, but we've defined I to be the square root of -1. Therefore, we say that I squared is equal to -1. So we can multiply this by -1 and get rid of the I, and then we just get AC minus BD plus BC plus AD quantity times I. Okay, now division is where it gets a bit complicated. So we have the equation A plus BI over C plus DI. Let's figure out how to deal with this. So I've got A plus BI over C plus DI. So if you remember the process of rationalization from Algebra 1, when you have a square root in the denominator, you multiply it by its conjugate. So we're going to do a very similar thing here. We're going to multiply this by its conjugate. So we're going to multiply by C minus DI. Then we're going to multiply here by C minus DI. Obviously, this should be fairly trivial in the bottom because I've got C squared. Then the cross term should cancel. C times DI minus C times DI, those cancel. Then I've got DI times negative DI, I times I is -1, so I've got a negative times a negative, so that's just plus D squared. And then we can deal with the top bit too. This is going to be a little bit less trivial, but it's just the solution that we got up here for the multiplication. So we've got AC minus BD plus BC plus AD times I. And all I did here was just separate this into some form real number plus imaginary number to make the complex number. So as you can see, it's not all that complicated as long as you understand the conjugation process for complex numbers, such that if I have some complex number a plus bi, its conjugate is going to be a minus bi. There's a pointwise representation that we'll talk about in the next video, which really highlights this, but we'll talk about that later. Okay, so here are these are the main properties that we need to know. It didn't mess up our algebra all that much, just a little bit of conjugation and needing to be very careful when foiling expressions. Okay, let's move on to the final topic for today's video, which is just a notational aside. So if I have the number a plus bi, then I can define the real part, re, of a plus ib is equal to a, okay? So this is essentially pulling out the real coefficient. This real operator is pulling out the real coefficient of the complex number to get the real part, okay? And then the imaginary part does the same thing, but we drop out the I because it's asking for the imaginary coefficient, not the imaginary part. Okay, so if we have that if the imaginary part of a real number, or of a complex number, is equal to 0, then that complex number, we'll call it alpha, is in the real numbers. Okay, so if a complex number has a 0 imaginary part, then it is a real number. So I hope that makes sense. So that is a little brief couple of slides to warm you up to the idea of complex analysis. Again, we're going to be staying mostly with the idea of the complex numbers as an algebra, first of all. So to give you a brief overview of this unit, what we want to do is we first want to look at the algebra, which we did today. Then we'll look at the point representation of complex numbers on the complex plane. Then we can look at how to represent them in polar form, exponential form. Then we'll look at the powers and roots of complex numbers, which is a little bit more complicated. And we'll move on to the concept of a planar set. Then we can move on to the function theory and the integral theory and the series theory. So thank you for watching, and if you'll notice, since this is more of a pure math course, we won't be doing as many examples until we get to more complicated material. The properties and definitions are very clear-cut, and we can prove them analytically without the use of examples in most of the time. If there is the need to do examples at some point, we will do that, but I'll stick to the theory for most of the first few units. Thanks for watching. We'll see you for video 2.